Hi everyone, today we're going to talk about differential heating, pressure systems, and wind patterns. Our first topic is differential heating on Earth. On a large scale, the energy is balanced on Earth, so therefore the energy coming into Earth and the energy coming out of Earth is equal. However, on smaller regional scales, there's an energy imbalance. This is due to the differential heating that occurs. So how different materials heat and cool. It occurs on large scales due to the differences in latitude, so the equator receives the most solar radiation and the poles receive the least. It also occurs on even a smaller scale due to the differences in land and water surface. Due to differences in energy received at the different latitudes, temperature and pressure gradients are created. These differences result in the creation of global and regional pressure systems and wind patterns. So, global pressure differences. Since the air is superheated at the equator, it rises and becomes less dense as the volume expands. This creates a zone of low pressure at the equator. At the poles, the air is cold and therefore it's sinking air in the zones of high pressure since the density is higher at the poles. It is important to remember the difference between the low pressure and high pressure. Low pressure is where air is rising, so therefore it's pulling up from the atmosphere. High pressure is where air is sinking, so it's colder and denser. So our global air movement is due to pressure differences on the planet. Since the air is less dense at the equator, it's under less pressure. It rises and moves towards the poles. The denser, colder air is then drawn in from higher air pressure areas to replace the rising air. These movements generate our global wind patterns. So if we look at the diagram on the right, here you will see the global wind patterns. Here's the equator, right here. It's an area of low pressure. The air is superheated and is rising. As it rises up into the atmosphere, it begins to cool down. So remember, as you go up in altitude, the temperature decreases in the troposphere. So as it rises up, it cools. Well, when it cools, it becomes more dense and begins to sink back down. So you end up having this Hadley cell here, which causes one of your wind patterns. Okay? Then up here in the polar high, you have a high pressure system because the air is really, really cold at the poles. So that's an area of high pressure. So it's sinking there. As it sinks, it gets pushed down to lower latitudes. It warms up and rises back up, gets colder, and sinks back down. Because of these two extreme pressure differences, you end up with this mid-latitude wind pattern. The air is rising up here, so the air that rises here gets pushed into the upper atmosphere, cools down, and sinks, creating this mid-latitude wind pattern. So this air movement due to pressure differences creates different areas of low and high pressure over the globe. The first one, starting at the equator, is the equatorial low. As air rises at the equator, it moves poleward, creating an area of low pressure because hot air is less dense and therefore rises. As that air rises, again it cools in the upper atmosphere, in the upper troposphere, sinks, and you have an area of a high pressure, which is your subtropical high. So as the air rises and moves poleward, it converges, cools, and sinks, creating an area of high pressure. Then we have an area of low pressure here, which is your subpolar low, in which warm tropical air is forced upward as it meets the cold polar air, forming an area of low pressure. And then you have a tropical high, which is the air rises from the subpolar low. It sinks, creating an area of high pressure. So now we're going to look at how the formation of wind happens because of these pressure differences. Well, winds are generated due to the mass air movements caused by pressure differences. Winds are generated moving in a general pattern from areas of high pressure to low pressure areas. The direction of wind is further affected by the Coriolis effect, where the wind moves in a 90 degrees to the right in the northern hemisphere and 90 degrees to the left in the southern hemisphere. This is a really good graphic of the formation of wind along the planet. Here you have the doldrums, or the equatorial low. This is the equator in which air is rising. As the air rises, it goes up into the upper troposphere, it cools, and then sinks. As it sinks, that air mass ends up pulling air with it as it goes back to the low pressure system. Remember, air goes from areas of high pressure to low pressure, so it gets pulled back, giving you the northeast trade winds. This is also your subtropical high here. So in a tropical high, air is sinking. So here we end up having the polar high up here. Let's go up this way first. Polar high, you end up having the polar high here. The air is pushing down. As it pushes down towards the low pressure system, it pulls that air with it. That gives you your polar easterlies. This is an area of a low, so the air is rising here, up through here, and then sinking back down to your subtropical high. As it goes back, it's pushed back up to the poles. You end up with your westerlies. The westerlies is what we live under, and it's caused because of these two air masses of the polar high, very cold air, and very warm air at the equator. So now we're going to focus in on just the westerlies. For the majority of our weather unit, we're going to be talking about the weather that we see here in the United States, which we live under the westerly wind pattern. So the first feature of the westerlies is the jet stream. So it's created when a polar air mass meets a tropical air mass, and it's creates a large temperature difference and therefore a strong pressure difference. This pressure difference generates a zone of strong wind high in the atmosphere known as the jet stream. The jet stream wind travels at velocities of 200 to 250 miles per hour. And throughout the jet stream shifts due to temperature changes along the United States. So here we have the jet stream and it dips down here. So we'd have a cold air mass. We often get these in January coming down from Canada. But then you'd also have this warm air mass of something coming up from the Gulf or coming up through close to the equator. And this band between these two pressure differences, these two air masses, is the jet stream. And this can shift and move depending on the season. So now we're going to zoom in even further to regional pressure differences. This would be an example of like New England or the Pacific Northwest or the Southwest. So the jet stream can determine the location of formation of a regional low pressure system that then moves eastward. Regional pressure differences are based upon temperature, albedo, and land surface. These regional pressure systems then move across the continent, generating our local weather systems. So regional high pressure system is known as a anticyclone, and a regional low pressure system is known as a cyclone. So the difference in anticyclone means that the air is sinking. So it's an area of high pressure as the air sinks down, and you have diverging air. Notice that this is a clear day. High pressure systems give us nice weather. So the air is sinking, therefore there's no cloud formation. In a cyclone, the air is rising up, forming clouds. This is a converging air mass as the air rises up into the clouds. So there's specific ways that wind moves in areas of high pressure and low pressure. They follow a particular pattern. Wind in a high pressure system always blows outward and clockwise. So the air is sinking and it's moving outward. In a low pressure system, the air is coming inward and counterclockwise. We'll deal more with this in a coming class, but just know it's counterclockwise around a low and clockwise around a high. So there's two terms that we need to know, isotherms and isobars. Regionally, differences in pressure, wind speed, and direction are based upon differences in temperature trends and pressure trends. Areas of similar temperature are mapped along curved lines known as isotherms. Areas of similar pressure are mapped along curved lines known as isobars. Wind direction can be determined based upon the movement from high pressure systems to low pressure systems. Wind speed is determined based upon the spacing between the isobars. Isobars spaced closer together result in a higher wind speed. So here's some examples of isotherms and isobars. Isotherms you've definitely seen before. They're on every weather report that I've ever seen. So here's an example of areas of equal temperature. And you can kind of, when you map them out, can see where the areas that are hottest in the United States and the areas that are coldest. And they color code them so we can see where those temperature differences are. Now, if we think back to jet stream and the areas of high temperature and low temperature, we can actually even see the jet stream when we look at isotherms. And it's pretty much following somewhere around here, right around where it changes from orange to yellow, because it dips way down and then it goes back up. So you can see where isotherms can be very useful in finding the jet stream. Over here, we have isobars. Isobars are areas of equal pressure. They can give us an idea of where a low pressure system's center is. And you've often seen L's and H's on weather maps or weather reports, and that tells you where the center of a low or a high pressure is. And we can notice they are always out in concentric rings. They don't overlap, so we always map isobars to be in concentric lines. Very similar to topography. So if they're closer together, the wind speed is higher. Where they are further apart, the wind speed is more gentle. Tells us how quickly the pressure is changing. Okay, so now we're going to zoom in even a little bit more. We're going to talk about land breezes and sea breezes. This is other types of circulation patterns. So daily changes in temperature of land or water can create local pressure gradients that generate local wind. So during the day, land heats faster than water. This generates a low pressure system over the land, so the air rises here, creates a high pressure system over the sea. Therefore, wind always moves from areas of high pressure to low pressure, so wind comes in from the ocean onto the land. You've often probably felt this when you're at the beach. That's why we go to the beach when it's hot, because there's that nice sea breeze that happens during the day. Keeps us cool, keeps the sea a little bit cooler temperatures. At night, this actually changes. Water cools more slowly than land does. Water holds heat better than land. That's why the beach sand is so cold when you walk on it at night. This generates a low pressure system over the water and a high pressure system over the land because it gets colder. Therefore, you end up with a land breeze at night. So the same thing happens with mountain and valley breezes as happened with sea breeze and land breeze. During the day, the heating of high terrain creates an area of low pressure here, creates an area of high pressure in the valley, creating a valley breeze as it goes up the mountain. It makes the summit often windy. At night, the steep slopes cool very quickly, creating an area of high pressure, causing the air to flow down, creating a mountain breeze into the valley at night. Okay, so at this point, you guys should make sure that your notes are complete and you can finish the whisk that is below this video and submit it for credit. And I'll see you guys tomorrow.